Mm. Yeah, thanks for the introduction. And my name is Jin Tan. As you just introduced me, I'm a principal engineer at NRAL. It's my truly honor and pleasure to co-present today with Dr. Xiaonan Lu, who is from the Purdue University for the UNIFI Spring Seminar. So together we will share our work on the oscillation studies of the Kauai Island power system on behalf of the entire Sapphire project team. So today I also have my key contributor, Dong, who is on the call with me. So this is a work that has conducted in collaboration with the KIUC, AES, and the Purdue University. In today's presentation, we will explore the oscillation challenges that introduced by the inverter-based resources. And we also would like to introduce you a very practical framework for investigating the real-world oscillations. Meanwhile, we would like to highlight some key lessons that we learned from the Kauai system. We are very excited to share our findings with the UNIFI community and look forward to the discussion. So before I move forward, Xiaolan, do you have anything you would like to jump in at this point?
No worries, Jin. Thank you so much. My name is Xiaonan Lu. As Jack already introduced, I'm an associate professor with Purdue University. Our team worked with Jin closely to basically mainly focus on the EMT-based small signal modular small signal stability and oscillation analysis tool. I will introduce the details later. So the floor is yours. Thank you, Jin.
Thank you, Xiaonan. So let's get this started. For this page, I would like to provide you a little bit of background about the challenges with the high renewable penetrations. As we know, it brings the challenges in many ways. One of the challenge is the new fast dynamics from the renewables, especially those dynamics caused by the inverter-based resources. So the lower figure we are showing here is the renewable penetration level keeps increasing in the past 20 years. And the upper figure shows the numbers of the SSOs, which is the subsynchronous oscillations that also happened in the past 50 years. And we could see that after 2000, the oscillation dramatically increased, which aligns with the trends of the renewables increase. If we look into those oscillations, so most of them are related to the fast dynamics of the IBRs, as I list some examples here. Just want to show you that those oscillations actually can cause very severe consequences like the blackout or even break down your wind turbines. So understanding and mitigation those IBR introduce the fast dynamics and oscillations becomes more important than ever. This is a world map that highlights several recent real-world oscillation events in the power systems, and such as those have already happened in the United States, Australia, China, and Europe, even the Africa. So the observed oscillation frequency ranges from 1.5 hertz to 30 hertz. If you look closely at this point, actually, this is our today's focus. You will find this Kauai island, which is located in the northmost major island of the Hawaii island chain. So this is where our study will be focusing on. In order to address a lot of different types of the oscillation challenges, our team has proposed a framework for investigating the real-world oscillation events. So it follows the following steps. So first, I think it's very important, which is get the event overview with the utility and the vendors and align those data's control actions with the frequency data by working with the utilities and the OEMs. The second one is the real data collections. No matter what data you can get from the field, if it's no matter it's the low speed or high speed digital fault recorder data or some other type of data, actually they're all very have play an important role in our analysis. The third step is called the oscillation source identification. This is more like the measurement-based analysis method. And we can adopt a different type of the methods to identify where is the oscillation source. After that, in order to gain a deeper understanding about the oscillations, we need to develop a full EMT model to replay the events. To gain insights into those root cause, we also think we need to do a small signal modeling and analysis that apply the model analysis or the frequency domain analysis to understand what is happening behind those oscillation phenomena. Eventually, all the work we have done here is to propose the mitigation method and also validate those proposed methods in advance so that we can avoid some potential oscillation will happen in the future. So this is the entire framework we have proposed. In today's presentation, Dr. Xiaonan Lu will first have an in-depth sharing about the small signal modeling piece. This is one of the main key methodologies that we have been used in this framework. And meanwhile, after that, I will share the examples, how we leverage this analysis or investigation framework to finally understand the root cause of these 19 Hz oscillations. In parallel, I would like to bring your attention to several things. So we have published this framework into several papers, I listed here. And meanwhile, we share a little bit of detailed in-depth investigations in the NRO report. In addition, I think we also, this framework or our methodology has been incorporated into a NERC reliability guidelines and also a ESIG report on the oscillation guidance. So you are welcome to find more related information if you are interested in our presentation and our recent findings. So with that, I think I will hand it over to Dr. Xiaonan Lu and to give an in-depth analysis or introduction about the EMT-based modular small signal stability analysis tool. Yeah, so Xiaonan,
sure. Thank you so much.
Take it over from here.
Yeah, thank you, Jane. Okay, I believe everyone can hear me clearly. If there are any issues, feel free to let me know. So as Jane mentioned, we have a whole oscillation event analysis framework, including different steps, and details can be shown with each step to identify a holistic framework. For our work, we mainly focus on the EMT models and also the small signal analysis tool to basically develop a modular framework to basically understand the system's small signal dynamics and also the potential oscillation modes in a scalable manner. Can we go to the next page? Okay, so basically we name it as a EMT-based modular small signal stability analysis framework. And definitely that means we started everything based on the EMT models. So we can dive into the granularity level and to achieve the modeling, to conduct the modeling of the entire system with the high fidelity of the different modules and the subsystems within the whole framework. Particularly, there are different steps we need to follow here. For the first step, definitely we need to get some data input, including the parameters of different assets in the system, such as the synchronous generators, the conventional rotating units, and also the inverter-based resources, such as the grid forming and grid following inverters, and the loads, as well as the network as well. And since we mainly focus on the small signal stability analysis framework, we definitely need to get the steady state operating point so that we can, derive the small signal models surrounding that given operating point. So the second step is to have the extended power flow calculation. And also very importantly, we need to dive into the modular small signal stability analysis framework. Basically, we have the block generation, meaning that we can generate those modular models of each unit, such as different types of IBRs like grid forming and grid following, as well as the synchronous generators, the loads, and even the network. And then we need to assemble everything. For the block assembly and integration plan, we basically have some information exchange among multiple units. So basically, eventually we can interconnect everything to form the entire scalable system model. specifically for the small signal stability models. And then we can focus on the outcomes of this tool. So basically, it is a small signal stability analysis tool, right? So the major focus is the stability-related analysis, including the eigenvalue analysis, model analysis to identify the critical oscillation modes, and to conduct the participation factor analysis as well. And also we can define some quantifiable stability indicators to incorporate these indicators in other grid operation tools or algorithms. So that is the major framework. And as we mentioned, this is a modular framework and a scalable framework, and we have different components included, including the extended power flow calculation, the modular models, and also everything is based on the EMT models. So basically, we can dive into the higher fidelity of the entire system. Can we go to the next page? Okay, so as a very brief background, as we must know that we traditionally focus on the physical layer of the power systems, including the network and also different types of resources connected to the network and also the loads as well. So this is a highly interconnected framework residing in the physical layer. And with the penetration level of IVRs increases drastically, we also need to understand that the operational dynamics becomes more complicated from the entire system perspective. So we also need to include the control layer dynamics and the integrated control layer dynamics with the physical layer to understand the entire framework. So this is actually a brief background, and our developed modular small signal stability analysis tool focuses on the coupled dynamics across the layers and consider different components and the major root cause of the oscillation modes in the system. Can we go to next page? Okay. Given that this is a UNIFI seminar series, I try to give a little bit about the background of small signal stability analysis first. So basically, since we are doing this analysis, it's necessary to consider some mathematical way to represent the model. So basically, the dynamics for a given system can be generally shown using a differential equation set. And just to simplify this differential equation set a bit, we can basically use a vector form to basically simplify this relatively full differential equation set, the whole representation there. And very importantly, for small signal stability analysis as the fundamental basis there, basically we need to select an acronym and also surrounding this given operating point in the steady state, we need to perturb the system to include some small disturbances such as delta X and delta U here. So with some general mathematical representations, we basically can understand the small signal stability analysis as something happening surrounding the given operating point, and to see with the incremental small changes like delta X and delta U, how the system will behave surrounding the original given operating point. So that means the original given operating point is showing there. So basically it is a steady state operating point, so it equals 0. And also the partial differential terms are also involved to identify the behaviors of the system along with the small disturbances delta X and delta U. And also the high order terms are ignored since they are really generated based on very tiny disturbances. So eventually, this whole thing can be summarized in matrix coefficient way. Basically, the derivative of delta x equals A times delta x plus B times delta U. So this is actually the general framework of some fundamental knowledge of small signal stability analysis. And definitely, everything started with the selected given operating point in the steady state, which can be named as XCUE here. So that's for the general mathematical background. Can we go to the next page? Thank you. So back to our approach, I would like to start with a comparison, comparing the conventional analysis and our proposed analysis. As we mentioned, everything starts with the steady state operating point. So that means we need to generate the current power flow to basically start the small signal stability analysis first. So with that considered, to compare the conventional power flow analysis and extended power flow analysis in our work, for example, for frequency, it is very different, since in conventional power flow analysis, frequency is generally identified as a 1.0 or at least as a constant. But in our analysis, frequency is a variable, since there are droop control or other kind of frequency regulation units there. And in the meantime, for the bus type, basically we have PQ, PV, and slack bus in the conventional power flow analysis. But in the extended power flow analysis in our work, basically we focus on the output characteristic of different types of buses. So it can certainly go beyond the conventional bus types and to follow the characteristics of each specific buses, even it is a droop controlled buses. Accordingly, for the power injection, basically for PI and QI, there are constants, generally constants in conventional power flow for specific type of buses. But given the complexity of different types of buses, basically for PI and QI, it can be shown as a function of omega and V here in our proposed extended power flow analysis. And also for the admittance matrix, they are varying, not any constants anymore. Basically, they are changing. They are varying based on the frequency. Since the frequency is changing, we also need to expand the Jacobi matrix as well to consider the partial differential terms with respect to the changes of frequency. Very importantly, at the bottom of this table, we mentioned the control systems. Conventional power flow analysis actually identified the P, Q, V, and theta, the phase angle in the physical network, the power network. But our approach actually extends beyond that, such as we mentioned briefly in the background slide. Basically, we also need to consider a whole bunch of control functions, since their operational dynamics intersect with the operation dynamics of the physical network. So everything is all included. Can we go to the next page? Thank you. So with this considered, we basically can use even the conventional Newton-Raphson method to calculate the power flow, but definitely the system has already been extended for sure with a whole bunch of changes we already incorporated. And then very importantly, we need to consider some specific things within this framework. First of all, we need to consider the control, the interaction of the control, and also the interaction of inverter interfaces. So circuit analysis is very important. For example, at least for the inverter interface filter, such as a common LCL filter, we need to understand how this part of the circuits can be considered within the entire framework. And in the meantime, for coordinate transformation, we may have millions of inverter-based resources, and it's common for us to use the rotating frame, DQ frame, for each one of the inverter-based resources. So that means we may have multiple DQ frames in the system, and they should be synchronized. So we need to select a common DQ frame, let's say denoted as a capital DQ frame, and we need to synchronize all the DQ frames to this common DQ frame to make sure that the coordinate transformation can be synchronized. And very importantly, back to the control diagram, just as a very simple example, even for the simple PI controller, it has an integral term, meaning that the system order is increased by 1 given the existence of this integral term. So that means basically we need to consider, no matter it is a steady state value from this integral term, the increased order of the system, or we also need to, and in the meantime, we will also need to consider the dynamics contributed from this controller. Basically, that's kind of like an integrated differential equation set with dynamics from the control diagram and the dynamics from the main power circuit. Can we go to the next page? Okay, now let's just use 2 simple examples to see what kind of modules we can develop. As we mentioned, this is a modular framework array, meaning that we do have, no matter we call it a library or multiple modules of the modular models we can use. Just to take 2 modular models as the examples. The first one is the models of the grid-forming IBRs. Basically, we are using a typical grid-forming inverter diagram as an example here. Basically, we have droop control, we have PQ calculation, we have droop control. We also have the inner voltage and current control loops, and also the voltage impedance control loops here. So basically, this is a 3-phase balance system, and the controls are implemented in the DQ frame. And we have omega P and VQ droop control functions. And definitely all the components are included, including the components in the control diagram, and also the main power circuit, like the LCL filters, as we mentioned, from power converters. In total, we have 6 state variables in the main power circuits, and also 7 state variables in the control diagram. So basically, eventually, we have the differential equation set generated based on the model in front of us. Can we go to next page? Similarly, as a common counterpart example here, this is for the grid following IBR. Also, we take a counterpart example here, which means that this is a 3-phase balance system, and the control is implemented in a DQ frame. And as we can see from the control diagram here, we have the dedicated power control loops, PI controllers for P and Q, active and reactive power. And also we have the dedicated controllers for the current control loops, as well as the phase lock loops as well. And definitely we consider the control diagram and the main power circuit to generate the entire differential equation set. So basically, as a quick summary here, to understand the orders and the scale of the system, we have 6 state variables in the main power circuit and 8 state variables in the control diagram here for the grid following IBR. Can we go to the next page? Okay, so with these 2 typical examples, hopefully we get an idea of what kind of modules, the modular models we can develop under this modular small signal stability analysis framework. Then let's take a look at some details. Basically, to delve into the details of how we can enhance the computational efficiency, we did a lot of things basically here. So as an example, let's take the power flow equations as the very simple example. This is actually not anything new. This is just the power flow equations. But the thing we need to do here to have something new here is to make sure that when the system becomes very large, when we need to embed this power flow analysis into our small signal stability analysis framework, we still need to maintain the scalability of the system. So what we can do is actually the question mark here. Generally, the very straightforward solution is we definitely can do some for loops or while loops to basically implement this power flow equations, right? So that's actually the straightforward solution on the left side. This is doable and this is straightforward, but actually the computational efficiency is not optimal. We actually can replace everything with matrix calculation, no matter in MATLAB or Python, no matter it is in commercial software tools or open source software tools. Basically, if we use matrix calculations to ideally completely replace the for loops and while loops, the computational efficiency can be significantly enhanced. So this requires some efforts to basically convert everything into matrix, and even with some, newly defined products to basically simplify the representation of matrix calculation. This same technique can also be used in some other aspects of the entire coding efforts, such as the Jacobi matrix calculation and among others. Can we go to next page? Okay. Since we are talking about a modular framework, basically we have each module developed. By saying module, we refer to the generator module, the load module, and the network module, such as the LAN. And the very natural next question is how can we assemble everything, basically to implement a relatively very large all-in-one model to represent the entire system, but still respect the modular configuration. This is actually an important perspective in this entire EMT-based modular small signal and oscillation analysis tool here. So basically for generator, let's say there are different matrix coefficients. Let's take this generator bus and assembling mechanism as an example. So basically for the matrix coefficient AG, we basically just place them in the entire system in the diagonal as the diagonal elements. So that's actually the easy way to place them in the integrated all-in-one large matrix. And then for matrix BG, BG, basically what we need to consider is actually the generator ID and the bus ID where generator is connecting to. So for example, when generator I is connected to bus J, basically BGI is placed at the entry of IJ. So that's actually the way for us to place the matrix coefficient BG into the integrated matrix. And also the next matrix coefficient is the BG omega, which is relatively easier. We basically just place them in the vertical vector. And also for the CG, the matrix coefficient CG, similar to the matrix coefficients AG, we basically place them as the diagonal elements in the all-in-one large A matrix. So that is actually the way for us to assemble the generator matrix coefficients into the entire matrix. Similarly, for load I connecting to bus J and also the network line I connecting bus J and bus K, we have similar approaches to assemble these matrix coefficients and generate the large matrices. Can we go to the next page? Okay, another very important and very practical issue is actually we need to consider the circuit connection basically when we need to integrate when we need to show the voltage representation of a single bus considering different matrices. As we can see on the top right corner, basically this is a very generic configuration connecting showing that a node is connecting to the generator, the line, and also the load. So basically, the bus voltage can be calculated in this way on the right side. You may notice that we involve an additional variable, which is Rx. The reason for us to involve Rx here is basically to take the full order of the entire matrix. Honestly, we take this Rs as a virtual resistance because it does not have any physical meaning. It's basically just to solve, to make the whole matrix and the whole equation solvable, to basically make the whole matrix a full order matrix. With that for that purpose, Rs is selected as a actually very large value. So eventually it can be ignored, but still it can give us the solvable solution of the system. And everything can be integrated into the matrix format as well with the matrix coefficients NG, ND, and NT defined here. And also similarly, Rx should be placed into the aggregated all-in-one A matrix, the big A matrix, considering, and when we need to do that, we definitely need to consider the IDs of the generators, the loads, and also the line, and also the lines, and in the meantime, also consider the buses and the bus IDs. So that is the way for us to consider the circuit implementation and how we can assemble Rx into the larger matrix. Can we go to the next page? Okay, so with all these efforts, you probably see that this is eventually the A matrix we are looking for. Basically, this is an A matrix combining the modular matrices from all the modules we developed in the entire framework, and a way of integrating all the matrix coefficients has been detailed have been detailed on the previous pages. Then, with this A matrix generated, basically we identified the entire holistic small signal models. It is implemented in a small signal way, in a small signal representation, using a small signal representation. Then let's take a look at what kind of outcomes we can get from this modular EMT-based small signal stability analysis tool. So first of all, for the outcome number one, or the output number one, this is actually very straightforward. Since we already have the modular small signal stability analysis framework, so basically we can identify the eigenvalues for sure. So that's actually the way for us to target the applications of stability identification or instability identification, and in the meantime also to consider the parameter sensibility of the control parameters or the physical network of parameters and identify their impacts on the system's small signal stability. And on the right side, for the output or the outcome number two, this is for the model analysis, which is kind of like a very natural next step of small signal stability analysis, where we can identify the oscillation modes and identify the critical oscillation modes in the system with the information of the oscillation frequency and also the damping ratio. Basically, we can use the tool to understand the oscillation modes in the entire system to get a clearer picture of the entire system in terms of the oscillating events. Can we go to the next page? Okay. Also, accordingly, we can basically we identify the oscillation modes. Very importantly, we need to understand what is the root cause of these oscillation modes or a specific oscillation modes. This is a question that can be answered by conducting the participation factor analysis. Specifically, we can have all the oscillation modes identified in the system, and the correlation with the state variables can be highlighted with a heat map generated by this tool. So basically, we can therefore understand that for each specific oscillation mode, we can understand which is the typical state variable that or the control loop that can contribute to this oscillation mode to stimulate this oscillation mode. That is actually the root cause of this oscillation mode. It can be something related to the main power circuit, and it can be something related to the inverter control diagram. This is the so-called the way to understand the root cause of the entire system, even considering the impacts of the control dynamics. And then for the fourth outcome, that is for the stability performance indicators. So here we refer to the quantifiable stability indicators or metrics. For example, as two very straightforward examples, we have the stability indicators of stability margin and also the minimum damping ratio. And these indicators can be also, generalized with different formats, and eventually we can embed them into the even the other types of grid operation algorithms, such as the small signal stability constraint (OPF). So that is the way for us to expand the horizon of this tool to basically embed it in other grid operation algorithms as well. Can we go to the next page? Okay, starting from here, I will quickly go through some case studies, and Jin will also introduce a very specific example later in his following presentation for the oscillation event analysis. Particularly for my work, for our work, the case study number 1 is for the computational efficiency enhancement. Basically, as you can see that we conducted the analysis of a whole bunch of systems with very different scales and sizes of the systems. And for each system, we identify the numbers of buses, generators, loads, and lines, and also incorporate the inverter-based resources there. Can we go to the next page? Okay, for the results here, as we can clearly see that with the increase of numbers of buses, actually, even no matter it is for the relatively simple testing or the very full testing to quantify the time needed for running the code. So basically, with our developed approach, comparing to the baseline, as we can see that actually the computational efficiency is enhanced significantly, especially for the right side, comparing the benchmark code MATLAB from a benchmark algorithm, which is MATLAB FSOL, and also FSOL with the Jacobian pattern, we actually can see that the developed approach can significantly enhance the computational efficiency there. Can we go to the next page? Okay, another quick example is for a two-machine system. I know this is a small-scale system, only 2 buses, 1 grid-forming, Joule-based grid-forming IBR, and 1 synchronous generator. But our developed tool can be used in this the small-scale system as well. We can use it to identify the oscillation modes, the major oscillation modes. As we can see that we have 5 oscillation modes identified here. As the very important one, the coupling one, we notice that omega and theta are the major dominant state variables related to this oscillation mode. And also, in further, we identified that theta is related to the troop control. So that can provide us the guidance for parameter tuning to enhance the system stability, to basically change the droop coefficient to basically enhance the system, to enhance the damping effect of mode number 3, the coupling mode. Basically, I also made the system more stable for sure. Can we go to the next page? Okay, and another case is actually very interesting one. I believe Jin has an extended version, so I do not dive into the details here. But generally, we have a relatively moderate scale of the system, 4 IBRs, 3 synchronous generators, 8 nodes, and 23 lines, which is not exactly the same, but similar to the Hawaii Island power grids. And in the meantime, we use our modular small signal stability analysis tool to basically understand the role of grid forming inverters in terms of enhancing system damping. Since this is a modular framework, our tool features a modular framework, so it is actually very easy to replace the grid following IBR module with the grid forming IBR module. So we have 4 IBRs. At the beginning, we have 0 grid forming inverters, only grid following inverters. We notice that the system is actually unstable, meaning that the stability margin is lower than 0 and the damping is negative. So basically, the minimum damping is negative. So basically, when we change it back to replace the grid following IBRs with the grid forming ones, and when we increase the numbers of grid forming inverters one by one, we can see that the system stability margin increases accordingly, and the system damping, the minimum damping increases accordingly as well. So that means the grid forming can actually enhance the damping of the system. Allow me to say that this is actually some conclusions we can get targeting this given system. It doesn't mean that the details will be everywhere the same. For example, when we do not have any reform inverters, the system is not stable. It's not like every system is like that. But the general trend is still something making sense. Basically, when we increase the penetration of reform inverters, the damping of the system can be larger. So that's a case of 3. Can we go to the next page? Okay, so as a quick summary, basically, as Jim mentioned as well at the beginning, our teams at Purdue and also Jim's team at Ariel collaborate significantly on this topic. And from our side, we mainly focus on the EMT-based modular small signal and oscillation analysis tool. These two papers basically summarizes the major details of this tool, the technical details of this tool as we just introduced. Can we go to the next page? Okay, this is not the end of the presentation for sure, and I'm just using this page to give it a pause, and then we can allow Jin to take over from here to introduce the specific example of Kauai Island oscillation event analysis. Jin is all yours. Thank you.
Thank you, Xiaonan.
Thanks.
So let's get back to this very specific oscillation event. Let's start with what happened on this island system first. So as you can see here, and we made an animation for this event based on the real measurement data. So on this map, the size of the circle actually represented the power generations, and the color represented the frequency. So below that, at 5:30 a.m., while most of the people are still in the sleep, we can tell when the largest generation was tripped. Actually, the grid lost 60% of the power supply immediately, and the frequency started to oscillate. And impressively, actually, if you notice that those IBRs, they have 4 IBRs actually provide a very good support during the whole event. But meanwhile, we also this can help them to avoid the blackout. But meanwhile, we also see these system level oscillations continued for 1 minute. So before we dive into the oscillations, I would like to give you a bit of background about the Kauai Island system. So this is not a big island, as I shown. It's located at the northern part of the Hawaii Island chain. And the first challenge is how they balance the system. And their system peak is about 78 megawatt recently. And also they have already installed actually 4 hybrid PV power plants, as note IBR 1 to 4 here along these island grids. And they do have the largest synchronous generator. That's what we call the KPS here. This is its location. So basically, they have a couple of the challenges to manage the grids. And the second challenge, the first one is how to manage the variability and uncertainty from the renewables. So KUC pairs the PV with battery actually is one solution for this challenge. And meanwhile, for the second challenge is this low inertia and the stability related issues. So to address these challenges, they decide to go with the grid forming inverter. So basically in 2018, they already commit a grid forming VSM in operation. And but for the rest of the three are grid following inverter. And in 2022, after the oscillation occurred, so actually they start to convert another grid following inverter. It's located here. We call it IBR1, actually converted to the Joule-based grid forming mode. So as far as we know, this is the first grid with a multi-vendor grid forming convention in the United States. So this is the background that I would like to provide to you. So in order to figure out what really happened, we have to conduct a very comprehensive study by following our proposed framework here. First, let me emphasize the importance of getting the first-hand field data, as we are showing here. Actually, at the very beginning, we get this direct analysis of the field data. Basically, this is showing the power output from the different inverters and the frequency data we got. Actually, it's still very messy. So we needed to do a lot of data processing and doing the Prony analysis. The key observations or takeaway messages here is, you probably can tell, first, this IBR4, which is the VSM grid forming, actually can respond really fast, faster than the grid followings here. Second, the IBR1 and 2 has the largest oscillation magnitude, and they are oscillate against the IBR4 and 3. Based on the Prony analysis, you probably can find out, okay, so who has the largest magnitude of this oscillation and who is oscillate against who. But the question here is really about, does that mean this is really caused by the IBR1 and 2, and how do we mitigate it, right? So the next step is what we call the oscillation source identification. So we compute the following by using following two methods. One is the dissipating energy flow analysis by using the phasor inputs, the PQ, theta, V. So how to read it? So if this energy is larger than 0, it indicates it's the source. So from this figure, we can tell the IBR1 and 2 seems like they are the oscillation source. Similarly, so we also compute the subsynchronous, supersynchronous power flows for each IBRs by using the point-on wave data. So for this one, if this indicator is less than 0, which means it's the source. So basically, those two methods give us a very consistent information, which indicate that the IBR1 and 2 were the oscillation source for these oscillations. At this point, we know who is the source, but we are still hard to identify what is the real root cause for the issues, right? So to dive deeper, actually, we need to leverage the EMT model. So we use the parallel computing techniques and build a full EMT model for the entire island grids. This helps us to explore the system behavior with greater detail. So from all the EMT study here, I would like to highlight two key points for this process. So first, why EMT modeling matters. So as you can see in this figure, the EMT modeling is essential to capture the 19 Hz oscillations that we observed. In the upper figure, actually the blue line is the actual recording. But when we first try to use the PSC, the result is obvious. The phasor-based simulation cannot capture it. So we go to the EMT part. But does the EMT modeling always be the answer? Not exactly. So even we use the generic model, build the whole grids in the EMT domain simulator, like the PSCAD, but still our PSCAD model couldn't fully replicate what is actually happening in the field. So this is showing that. So recreating the actual system behavior is still very challenging, even with the EMT. So this is lead us to another question. So we have to, in order to improve the model accuracy, we have to work with KIUC engineers and the vendors to obtain this vendor model. But the question is, are vendor model always the accurate? Does that directly give us the answer? Not quite. So in our study, we integrated the real world data into this test system, and a lot of the point of interconnection actually can see the same grid conditions as it is in the field. And we compare the simulated data against the field data. And this is what we have found out. So in this figure on the left, the blue line actually is showing the recorded data, and the right one is the simulation data. So you can see they still don't perfectly match what actually happened in the field. So here I would like to emphasize one thing, which is the model validation using the real world data is very crucial. It's essential to validate the model at the plant level using the actual disturbance. It's not to see the vendor provided model is not good enough. It's just sometimes when you implement it, it still has a lot of uncertainties. So this model validation procedure will be highly recommended to ensure their fidelity and the reliability under the real operational conditions. After all the efforts we put into building this full EMT model island, so now we can see a pretty good match in P, Q, frequency, voltage. So we are happy with that. At this point, we could try a try and error approach by tweaking the parameters here and there, but this couldn't give us the full pictures of the oscillations. So that's why we propose, hey, why not use the small signal analysis to help us to better understand the nature of the oscillations and uncover those reasons behind it, the root cause behind it. So as Xiaonan already introduced previously, here, the Purdue team has helped us to develop this EMT small signal analysis tool to identify those key parameters and how they affect those critical oscillation modes. Due to the limited time today, I think I probably need to cut our presentation a little bit short. So here, I just want to emphasize that by using those small signal analysis tool, we do identify that, go to the controller level, find out that the PL gain and the PF droop actually is really relevant to our oscillatory mode, these 19 Hertz oscillations. So this tool is very valuable, but sometimes you also may ask, hey, but it's really hard to conduct a small signal analysis based on the vendor model because they are the black box model. That's where this frequency scanning as a approximate techniques is very efficient to analysis this subsynchronous resonance, as it's not required detailed IBR models. So here, just want to give an example that we perform the frequency scanning techniques of the EMT model and to visualize the impact of frequency measurement delay on the Nyquist curve. If you know that, so this is indicated it's stable, but when it's circled -1 on the real axis, actually it's become unstable. So in that case, we also perform this frequency domain analysis by perturbing the different parameters. Here, we finally we did a lot of tries, and Xuan actually identify the final kind of like the root cause of the entire oscillations as we are showing here. So what it is. So basically, this is very important to note that it's not a single factor issue. The oscillation is influenced by the multiple interaction factors. So for example, we find it out, and basically, if we lose a synchronous generator, definitely this will make your grid become weaker. And it makes more challenging for your grid following to maintain the stable, right? However, there are several key measures that we can take that probably can help us to mitigate that in advance. For example, if we can reduce the frequency measurement delay, if we can lower the PLL again, if we can adopt a less aggressive PF droop. So all those things will be helpful, and maybe we can take the actions even in advance. So in summary, this is telling us it's not just caused by a single issue, and it also caused by the multiple issue. Even we can recommend we can use a smaller delay, less aggressive PF droop, or make the grid stronger, or use a smaller PL again. So eventually, we also propose this lookup table. We think this will be easier for the kind of engineer to use it, especially sometimes we may don't have enough time to run the simulations, but this can give a general idea. Basically, we know delay we won't be able to change, grid strength we won't be able to change, but at least we can change the PF droop. So how can we change? How can we properly design the PF droop constant for our system operation to avoid some oscillations in advance? So I probably need to skip those things and directly talk to the mitigation methods. So recall that we have mentioned a couple of the mitigation methods, including less aggressive PF droop, use a smaller PL again. So you can comparing the mitigation method, which is shown in blue. So you can see how the performance looks like while we adopt the mitigations that has been proposed by our analysis. Another important one, this is a very comprehensive replacement study that has been conducted by Xuan. So basically, he replaced the upgrade the grid following inverter to the grid forming one by one at the different location. So the main takeaway message for this one is we find out no matter you change it to droop-based grid forming or the VSM, actually they are all very helpful for mitigate these 19 Hz oscillations. Eventually, I think this is a very exciting moment, but not a good event. I mean, not for KIUC, but you recall that the KIUC converted this IBR1 to the grid of droop-based grid forming in August 2022. But on April 2nd, 2023, there is a very similar event happened again on this island grid. I swear we didn't made it up, but it happened. And this is become a very natural kind of like a proof to see how effective the grid forming to help to stabilize the grid after the largest N-1 contingencies, and you didn't see the oscillations anymore. So this is another example showing that how do we use the why the grid forming actually can provide additional support, including enhance the grid strength. This is a video that I probably won't be able to show the full things with you, but this is telling us nothing happened in this grid. In a summary, so we proposed this oscillation event analysis framework for the real world power systems. And we did the analysis by using the measurement-based method, the model-based method, and we identified the root cause for these 19 Hz oscillations. Beyond that, we also proposed the mitigation methods, and we provided two tools. One is the EMT-based small signal analysis tool. One is the simple lookup table as a tool for the planner and operator for the stability margin check. And at last, I know I'm already over time 1 minute, but I do want to thank our main contributors to the whole oscillation work, including Xuan Dong, who is conduct amazing oscillation study for the entire 19 Hz oscillations for KIUC, and Cameron provide a lot of data, and Li Zhiding, who helps with this small signal analysis. At the end, I provide you some papers and the reports reference here and for your further readings. Thank you very much. And yeah, I don't know if we still have the time for the questions today.
Yeah, I think we have some time for questions if anybody wants to put